So first, I'll just lay out what the general process of going about a hypothesis test is. Like, so hypothesis testing is just testing, like when you're talking about hypothesis testing in terms of statistics, it's usually of the type that does the sample belong in this population? Are both of these populations or both of these samples from the same population? So are they equal? It's usually to do with comparison of means or sometimes standard deviation. So the general steps that you take for hypothesis testing is, first you will state a null hypothesis, which is usually of the type, usually of the nature of there is no variations, like innocent until proven guilty types. So you will assume there is no variation. Both of these means are equal. Now the alternate hypothesis depends on what exactly you want to do. So let's say, we have in our UNCIA data set leopards from two different locations. One is Wuhan and one is, I forgot, but the second, you're mute, Guillaume.
Doing that. The Vacan and Altai.
Sorry, no. Okay, Vacan and Altai, correct. So maybe one of the things we want to do is test if the leopards at Vacan and Altai are the same size or not. So one way of testing it would be saying that, okay, you want to just see if the sizes differ. In such a situation where you don't have a prediction either way, what you would do is a two-tailed test. So the alternate hypothesis is simply that the two population means sample means are not equal. But let's say you had some reason to believe that the leopards from Vacan are bigger than the leopards from Altai. That's where you would do either a left-tailed or a right-tailed, depending on which way your prediction is going. So if you want to test if the Vacan leopards are bigger than the Altai ones and Vacan is mu2, your alternate hypothesis is going to be mu2 is greater than mu1. And if it's the other way around, you want to test if the Altai ones are bigger than the Vacan leopards, then you would do a mu1 is greater than mu2 test. And this is simply to say how you would interpret the results. Like the actual application of the test will not vary based on what your alternate hypothesis is. How you interpret the results is what will vary. So once you have your null hypothesis and your alternate hypothesis, what you will do is set an alpha, which is the level of significance. And as most of you probably know, the level of significance for most scientific tests is set at 0.05. So, and how this is applied is, once you calculate the test statistic, whatever it is, this is how it used to be. These days, R will just give you an output and tell you what your level of significance was. But earlier, what we had to do was look at a critical value table. So how the table would the interpretation of the table is, you would look at the row, which is equivalent to the degrees of freedom of your sample. So let's say we had 16 samples, and our degrees of freedom is 15, you look in this row. And you would look for the corresponding level of significance that you set. So if we set 0.05, the value there is 2.13. So if our test statistic is greater than 2.13, we can say that it was significant at 0.05 or greater. But if it is lower, then it's not. And how that interpretation, so if you find that your test statistic was greater than the level of significance and appropriate sample size that you looked at, then what you do is you will reject the null hypothesis. So all you're doing here is, this is where the distributions come into the picture again, just to show. So when you set a level of significance at 0.05, what you're doing is you're just drawing a line here. So that's like 95% of the data, and you're looking at whether the test statistic lies this side of the distribution or on this side. If it's on this side of the distribution, the null hypothesis is true. It means that these means are equal to each other. But if it falls beyond the level of significance that you applied, then you reject the null hypothesis and therefore state that the two population means are not the same. Okay, and the whole two-tailed, one-tailed thing is, if you're looking at just if it's difference, then you will levels of significance on both ends of the tail and look at if the statistic lies on either side. Or if you're only doing a one-sided test, for example, if you wanted to see if Vacan is bigger than the other one, then you draw the line only on one side. So because it has to be 0.05, it will be slightly ahead. Otherwise, you will draw at the 0.25 mark on both sides of the distribution. Okay, so this is clear, correct?
We can maybe repeat the steps one more time to be sure.
Yeah. So you just state your null hypothesis, state your alternate hypothesis. And technically, what it is doing is creating the test statistic will have a just testing how far apart, like if you're testing if both of these means are equal to each other or not, it's looking at how far apart these means are. So let's say if mu1 is somewhere in the middle of the distribution, it's looking at how far from mu1, mu2 is. Okay, so if it is far enough away beyond where you had kept your level of significance, you can say it is too far for it to have just been by chance. And therefore, you will reject the null hypothesis. And so technically in statistics, you will never accept the alternate hypothesis. You can only reject or accept the null hypothesis. But for all practical purposes, we know what it means. Like, so that means that the means are not equal.
Right.
Okay. All right. So then we will now do the t-test, which we will apply to our data. But before that, I'll just explain what it does. So a t-test is basically very similar to a z-test. It's just that z-test is only applicable when you know the sigma of the population that you're testing for. If you don't know the sigma, which is usually the case, what you have to do is apply a t-test. Okay. And so this is the difference between the t-test and the z-test basically. So the t-test is dependent on the sample size. That is one thing. And while the z-test is not, sorry, yeah, the z distribution is not. The t distribution is like a little flatter and higher than the z distribution. So more data points will fall in your rejection, like away from the mean than it does for the z distribution. But this peak tends to increase as you increase sample size for the t distribution. So beyond a certain sample size, the t distribution does mimic a normal distribution, that is z. So like beyond a certain sample size, usually they say 30, you could apply either z or t. It doesn't matter too much. And there are three types of t-tests that you can apply. There's the one sample t-test, two sample t-test, and paired t-test. So one sample t-test is when you want to compare your sample to a known population. So you have to have a population parameter in place. So for example, let's say that somebody sampled a particular mountain range and found that the size of the leopards there was an average of 110 centimeters. So since you already have an estimate for the population and then you go there 15 years later and sample the leopards again, and you want to compare if the leopards have gotten bigger or smaller, what you would do is the one sample t-test, because you know, or you at least have a population estimate mean that you want to compare it to. When a two sample t-test is when you have two samples and you want to compare. For example, the comparison between Bakan and Altai. You want to see if the leopards in both of these sites are the same size or there's a difference in size. What you will do is the two sample t-test. And a paired t-test is when you sample the same individuals and want to see the difference of a treatment. So, you know, let's say everybody was diseased in a certain area, you sampled their sizes or their weights, which was a certain, and then implemented a strategy for curing of disease or increasing of nutrition. Then you sample the same individuals post-treatment. So basically the two points are independent of each other. They're just the same individuals before and after a treatment. What you would do is a paired t-test. And these are the one of them. So if you look at the equation of this one sample t-test, which is this first one, you'll notice it's actually very similar to our z-scores transformation. It's because it's doing the same thing, but we are applying it in a smaller data set and not knowing the standard deviation. So it's just minusing the population mean from the sample mean, dividing by standard error. And it's a variation of the same for both two sample and paired t-test. Now, the assumptions that you have to be fulfilled for you to be able to apply a t-test is that the data points are independent. So like we mentioned earlier, the data points cannot be biased or correlated in any way. They have to be randomly sampled. The data has to be approximately normally distributed. That is when you would ideally apply a t-test. But like we mentioned earlier, there is some leeway here. Like t-test is pretty robust to violations of this assumption. But generally speaking, it's good practice not to apply to something that's too far from a normally distributed, approximately normal distribution. And especially in the two sample t-test, this is very important. There has to be homogeneity of variance. So the samples being compared have to have somewhat similar dispersion around the mean. So if one sample is like really tight around the mean with very low standard deviation and the other one is different, then that is the assumption that t-test is not very robust against violation of. So this you have to really make sure before you can apply a t-test. Okay. And so now we will move to R and sorry.
Yes.
Try to apply this to our data set. So has I hope everyone calculated the BCI. You can start sharing screen.
And it's okay if you did not, because we'll do it together.
Yeah, we'll just do it again.
The main question is, did you manage? Like, can you say in the chat if you managed to calculate BCI yourself? And if not, maybe you had errors doing that. So Priya tried. Does that mean you didn't succeed?
Okay.
Okay, so of course there's.
I did for this ratio, like Vani and I, we together did for like ratio, like mass and length.
Yeah, so mass divided by body length, the first one that I put in the table.
Yeah, and then log transformation also we did. We both did together, so yeah.
Okay,
I don't know if it's right or not, but then yeah.
Someone did BCI log also divided by log. Okay, cool. Okay, yeah, that's also I think the same one that a lot of people did. Of course, if you looked at the paper and the table, a lot of some of these indices we could not apply because we didn't have some of the data that you need to do that. Like I think those things like hip, some body measurements that of course we don't have. I put two in the table that you see here shared on the screen. These are the ones that I will demonstrate, especially for those who didn't manage, in case you didn't manage to do it. It would have been, and there's a lot of them. The others that are very similar, where you take like a squared version instead of a log, you take the squared or the cubic. And there are other methods which I think we might demonstrate later when we do regression, which it's a bit more advanced, so I didn't apply it here. Although I do think that it's maybe a better index to use.